Okay, this video is really big. I can put those things up, and you can see the blocks are like much smaller. But again, one thing to notice as a contrast is that like at high quality, and also when motion is already high, you see that the I and P frames are kind of similar. Like it's not, just doesn't make much of a difference. And it's also reflected in the file size. Like we saw that just iframe compression on this video takes 9 megabits per second, while INP takes 6 megabits per second. So it doesn't help as much in this case, right? And yeah, it's quite seen here. It's just because we are relying on the P frame, like the residual to be sparse for good compression. But if there is a lot of motion, and if the motion is like kind of weird, then we might not be able to predict the next frame as well based on the previous one. And so then you will be using a lot of bits. Yeah, and I think it should be, if we view the motions, it should be quite, so this is the first frame, but again, I mean, if I zoom into it, it should be quite obvious. But again, here also you see it does flip, like the iframe, INP versus, and the split is different, but the iframes still take a bunch of space. That's what it looks like. All right. Okay. Yeah, so this is the P frame video. Any questions as of now? Is the StreamEye demo fine? Okay, so another thing which I wanted to do is just open up this file again in media info. So I mentioned media info is a quick tool which you can use to like view things. And I showed the raw file before. So now we can look at the encoded file. And you can see a bunch of things here, like there's advanced video codec. Advanced video codec is another name for H.264. It used to be advanced 10 years back. It's not as advanced today, but yeah, anyway, that's the name. And so you will see AVC also put in the files at various places. And again, another thing which you see, like the stream size is 3.16 megabits. Let's see where is okay, so this is the bit rate. Bit rate is 6 megabit per second, which is what we had seen earlier. And you see a lot of settings here, encoding settings. And you will see that this is metadata, which is the encoding settings. So like FFmpeg internally does a lot of options while encoding this file, and you have the manual control to change these things. Like for example, it uses SCABAC, which is adaptive arithmetic coder, instead of Huffman, or it will use look ahead, like while finding the motion. Because in case of P frames, like one P frame also impacts the next future 8 P frames, for example. And so you need to look ahead to see what the motion is and so on. So you can do all sorts of optimizations to improve the compression. And that kind of makes the encoding much slower, but sometimes better, right? Yeah, so there are just a lot of options which you can look into. We are not going to try to understand anything of here today, but it's quite interesting to see that. Yeah. Cool. Okay, so another one thing which you could ask is that why restrict us to this kind of a coding where we just like start with an image, like we encode one frame independently and then encode the next frame conditioned on that one and then go on. Instead, what we could do is that because this is kind of extrapolation, like you are taking one frame, you are extrapolating it to the next frame and then encoding the difference. Typically in real life, we know that interpolation works better. So why not do it that way? So let's just have one image frame. Let's predict this P frame based on iframe, like here. But then the intermediate 2 frames, let's interpolate between frame number 1 and 4, right? And that, potentially, because this P frame is further away, it's like 3 or 4 frames away, there will be much more motion and the P frame could cost us more bits. But these the frame number 2 and 3 here could basically could be much simpler. The bit rate to use them could be much simpler, much smaller, right? And so this is called B frame encoding. So the B here stands, I mentioned P stands for predictive coding. The B stands for bilinear coding because it references both left to right directions. Right? Yeah, so again, we could do this. And in fact, if you encode your video, when you upload a video on YouTube, or most of the times, videos nowadays are actually encoded using B-frames. In fact, I'll come to that. There's something called hierarchical B-frames, which is what is used. But B-frames is what is used for encoding most of the like videos which you watch on Netflix or YouTube and so on. Right? And the main reason why this works better is just interpolation versus extrapolation. That interpolation is a much simpler problem. So if you have one frame here and one frame like ahead, you can interpolate between them quite well. Yeah. Cool. Maybe, we know that it should lead to better compression, but let me again show you that. Again, maybe we'll do that later. But any thoughts on when you might want to use, like in some cases, INP frame coding might be better, like in some applications. Any thoughts on when you might prefer INP frame coding versus IPB frame kind of coding? Yeah, okay, so the hint is that, in compression in this class, most of our concern has been just better compression, right? But at the same time, in real life, a lot of times there are other constraints like speed, latency, and so on. And so those constraints come into the picture. Like for example, with the B frame, let's just say you want to start looking at this video, right? Now, if you want to, the frame 1 will get decoded quickly because it's an independent image. But to decode frame number 2, you first need to decode frame number 4 and then decode frame number 3. So it adds to this latency. It adds to one frame latency, which in some cases is okay. In some cases, it might not be. Like for example, if you're doing real-time video calling with someone, then it might be prohibitively. First of all, you don't know what is this future frame. You can't just wait for n number of frames until someone talks and then encode. Otherwise, like the Zoom talk is going to be delayed. Like everyone is going to receive delayed frames. So it's just not possible. And so you will see that like Zoom chats or like whatever, Google Meet, FaceTime, all of those use INP style coding. Well, at the same time, Netflix or any kind of video on demand uses B-frame because there it's okay, there it's fine. You already know the entire video, and so you can encode using B-frames. And so you might have seen that if you're watching on YouTube, if you try to seek to some point, it might not start from that exact point. It will go somewhere like towards the left or towards the right or somewhere, right? So what happens is that it syncs it towards the closest iframe because it can't start decoding at some arbitrary points. It has to start decoding from an iframe. And so if you go to YouTube and try to seek to some arbitrary point, it will maybe not start at that exact point. It will go somewhere left or right. Yeah, is the B-frame clear right now? All right. Yeah, so this is what I was mentioning, that B-frames is like low latency kind of settings for video conferencing. I plus P plus B-frames. It's also called random access mode, again, because it allows you to, it's a slightly misnomer, but it allows you to get much better compression at the same time seek at various points. At the same time, you will see iframe compression is also useful, and it's actually useful in video editing softwares. So if you have used ProRes, or if you have one of you is a YouTuber, then there are these mezzanine formats which encodes the video. And the reason is not to save space on the file. It's just that to make this editing at least possible. Like if the file size is like few gigabytes, just editing an image is going to be crazy. So what it does is that you compress every image independently. And so if you want to edit this video, you can load one frame, you can do operations on it, put it back, and so on. So it just makes it more possible. So the iframe compression is also used more as a intermediate step when you are processing the video. Cool. All right, so I also wanted to show, maybe let's take a look at another video, which is again B-frame based encoding. Again, we'll select our second favorite video, the foreman. Yeah, and again. So again, another thing here. So maybe again, it should be possible for you to guess based on the bit rates here. What is the frame structure? Like which frames are P, which frames are B, which frames are I? Any idea? What is which frames? Like which frame is P, which frame is B? In this case, based on the bit rates. Yeah. Yeah, okay, so I'll give the hint. So these two are iframes because I mean they take a lot of space, so I'm guessing that they are iframes. And then there's a slight peak here, and there's a slight peak here. So these are most likely P frames, right? Predictive frames, we are predicting ahead. And then all these three in the middle, these are the B frames which are encoded, conditioned on this one, based on these two. So these are the interpolated frames, and as you can see, it takes much lesser space than this one. Yeah?
It says that there's 4 P frames though, right? On the left side of the menu.
There are? Sorry, what you're saying? 4 P frames. Okay. Okay, so let's see. There's one P frame here. There's one P frame here. Yeah, sorry. Okay. Okay, let me see. Where are the P frames? So we can also look at this dependency structure graph here to know what is happening. Right. So this is an iframe. This is an iframe. And what are we predicting? So this is a P frame. Oh no, this is a B frame. Right. Yeah, so I think it's encoding. If you look at this curve, then this is a P frame. This is also a P frame. This is a P frame, and this is also a P frame. That's what it looks like. So again, we can look at the decoding order. So first, this is the video. The second frame is this one, which is decoded based on the first one. Then it decodes these ones, right? Now it decodes this one. This probably might be, I mean, I'm not 100% sure why it does that. Maybe because it found like the iframe, it also depends on the encoder, like what we do. Again, this is the P frame, second P frame, right? Again, we do B frames. Again, third P frame and fourth P frame. This potentially could be, I mean, the result of the encoder deciding that there is some kind of a scene cut at this point. Like maybe these two frames are slightly different. That's what the encoder decided. Yeah, but yeah, they are right. So, I mean, we were correct on that part, but there was another P frame here, which is in here. And it's easy to see based on also this dependency graph, which tells us like which frames are being referenced and so on. Right. Yeah, and again, it's interesting to see the size, like for IAP versus B. You will see that, I mean, even if the B contains most of the number of B is just higher, the B files contain much lesser in terms of proportion. And another thing which I wanted to show is that actually you will see that in some cases, like you will see the frames referencing more than 1-2 frames. Like the B frame need not reference just 2 frames. Like for example, here it's referencing 3 frames. So that's another something the codec can decide. Like it wants to reference the P frame and the I frame, but it can also reference other frames in there, which other P frames which are in there. Yeah. Cool. All right. So we can also look at our jockey video here. Yeah, I mean, again, it's slightly weird because it remains, even if I'm encoding with B frames, the encoder decides that because there is a lot of motion, it doesn't make sense to encode using the B frames. And so you'll see that, at least in this case, I'm seeing that it's all P frames. We'll see a go ahead. In the first thing, it's all P frames, right? Here it's, again, P frames. And then okay, there are some B frames here, right? So even if we specify to the encoder that I want to use IP B frames, it need not use them. If the motion is a lot more, it might just think that it's probably okay to use I and P frames in this case. So just to summarize the motion encoding, basically the block-based searching and the encoding which we discussed is kind of extremely efficient, but at the same time it's very axis aligned. So it's very similar to BPG and JPEG. It will produce these blocky artifacts, which you will see if your video sometimes your bandwidth drops on Zoom or something, you will see a lot of weird blocky artifacts, and that's mainly because of these algorithms. And so these algorithms also need these deblocking filtering, which is part of the loop, which does some post-processing to kind of make the video look slightly better. But I mean, a lot of time it just doesn't work because there is just so much of blocky artifacts that it typically might not work. Cool. All right. So I just wanted to quickly touch base on how there have been in parallel literature on going from traditional video coding towards machine learning based video coding, right? And we did this exercise in the class where you took JPEG and transformed it into a learned image coder, right? So we could think of in that same lines, and maybe the first thing which you could do here is that let's keep this motion based block alone. We know that we have a learned image compressor. Let's just try to replace the the traditional image compression pipeline here using ML based coder, right? And so that obviously could give you much benefits, but at the same time, if the entire thing is trained machine learning based, then it could also give benefits. And the reason is that the flow quality might be better, like the motion quality might be better. Instead of using block by block, you could have motion which is much more smoother, and that can give you much better benefits. Right? So I just wanted to show some. So this is again a few years old video, or so you have. If you use block-based searching, your motion is something like this, but learned techniques can have much smoother video because they are a bit more stronger and they can have a bit more biases built into it, right? And that typically can lead to less artifacts. So for example, here is H.265, which is one generation ahead of H.264, and you see that there are a bunch of these blocky artifacts in here at lower bit rates, while ML-based codecs are a bit more smoother as compared to H.265, right? Yeah. Okay. And so there has been a lot of work. Again, this is a few years old. There has been a lot more progress, not as much on the PSNR-based metrics, but on other metrics. But you see that the ML-based codecs are already much better than, say, the purple curve is the H.265. And it's much better than that. AV1 is a newer codec which is already part of some of the machines, but not adopted everywhere. But it's also better than that, and things have improved since then as well. At the same time, the one thing which we saw in the image compression class is that it's not very easy it's very easy for a machine learning based codec to optimize for a more complex metric. Right? And so if we take the metric as, say, MSSIM, which is a more perceptual based metric, then ML based codecs have a much higher advantage and they can do much better. Right? And so that's what we see here. And so that's where maybe the future is going towards, that video based coding, what we know now, H.264, 265, is kind of simple. It works, but at the same time, ML based codings can do much better. Yeah. But at the same time, there is a lot of trade off, because I mentioned that another constraint is that video decoding or video encoding needs to run in real time. Like you are running these things 30 FPS or 60 FPS on your machines, and so it needs to run extremely fast. And so that's the reason why you can't really rely on, using a machine learning model which is crazy big, like one of the large language models, large video models, it might not work on your machines because it definitely won't run in real time today. But of course, with a bit more of effort, it's possible to run it real time at some point. Yeah. Cool. All right. Thank you. That's it. Any questions? Okay, I'll hand it over to Shubham for the rest of the talk. So just one final thing which I wanted to mention. So yeah, my team at Apple is hiring, We work on various problems on both, ML-based image and video processing, compression, and so on. So yeah, if you're interested for both internships or full-time roles, do send me an email. And yeah, that's it. Thanks.
Thanks, Kedar. Sadly, I can't say that the compression team at Amazon is hiring, but yeah. Okay, so concluding just a short sort of summary of what we have learned together. And so in the early days, a couple months ago, we started looking at very simple IID data, right? We did some theory, the first few lectures. We learned about entropy, and then we defined prefix-free codes. We looked at a few specific examples of prefix-free codes, Huffman codes, arithmetic codes, RANS, and as you might have seen, like since then, both in the first half and in lossy compression, these are like fundamental building blocks, right? Even today, Kedar mentioned CABAC, which is like a very efficient arithmetic coder, and so all of these are used. Even if your data is not IID, right? You can transform your data in various ways, get to something that is almost IID, and then use one of these basically. And we saw all of these have different trade-offs in terms of how close they get to the entropy and how efficient they are in encoding and decoding. Right, and then the other thing we looked at in the first half was fundamental, and also in the second half, but in the first half we looked at entropy, which is the fundamental limit of compression. This is one thing I've really liked about compression in the years I've worked on it, is that the theory is really, theory really helps you out in practice. You can use the theory, especially for lossless compression I've seen. You can start with the theory, make a model for your data, get some numbers, and then actually compare what you're getting in practice with the numbers, and that gives you a lot of insight. And not only that, actually some of the tools from information theory are used beyond just information theory, because if you remember the result, like the fundamental result for lossless compression, where we showed that no compressor in the world can do better than entropy. It's a very strong result. It's like non-trivial to prove results where any algorithm in the world cannot do better than something, right? And it's used in various places. You're actually getting a glimpse in the find the best rower problem this year in homework 4, right? So, and the last thing we saw in the first half, the last 3 lectures basically, was non-IID data, or what we call real data, right? And so one key idea we learned was, we looked at entropy rate, we looked at conditional entropy, and then we learned that a good predictor gives you a good compressor, and a good compressor gives you a good predictor, right? And we saw some different types of models. We saw kth order adaptive coders. Many of you, some of the projects you are doing, there are a few projects on context tree weighting, PPM, which are more advanced predictors, right? And we also had some fun. This was very new this year with the llama models and so on, to look at how LLMs, or very powerful predictors, can be used as very good compressors, right? And then we saw universal compressors, right, where you don't even try to model your data explicitly, or it's very implicit. Basically, you have a compressor that achieves the entropy rate for any stationary source, right? And we focused mostly on LZ77, but we have projects on both LZ77 and on LZ78 as part of the projects. And the last thing we did in lossless compression was we looked at some tips on how to use lossless compression in practice, right? So in future, I would suggest whenever you have a problem in your research, at your job, whatever, right, you want to compress something, take a look at those slides, right? Because oftentimes we see that people who are now that you know compression, you should, if you remember, if you did that quiz question, right, where you are asked to build a compressor for your company and what do you do, So yeah, always start from first principles, right? Before you do anything crazy, evaluate the thing, understand how is Z standard doing? Do I have a model of the data? Can I compute the entropy? Is there a gap between what a standard compressor already gives me and what I want to get to, right? Don't just like start writing your own compressor for every file you get, right? And so one key idea which kept repeating in the first half and also in the second half is that however complicated your data looks at the first glance, what you want to do is you want to model it, you want to transform it into something that can be used with standard compressors, right? Try to reuse the tools. Don't re-implement your Huffman coders and your arithmetic coders and your LZ77 coders. Of course, for projects you do that, that's fine. But like in real life, right? You want to use tools that exist. And then we switch to lossy compression, right? So mostly Pulkit, today Kedar, and Tsachy talked about it. So we started with some fundamentals. We looked at quantization, the simplest form of lossy compression, scalar quantization, uniform scalar quantization. We looked at rate distortion theory, which is like the corresponding thing to entropy. And we understood like the fundamental limits there. And then we looked at vector quantization, and then we looked at transform coding based on the intuition with, we looked at that eigenvector decomposition and tried to understand how to decorrelate the input, right? And we learned about DCT, which is like a transform that works really well for images. As you might have seen, or if you didn't see now, you will see later if you like ever try to use this, is that the theory for lossy compression is maybe not as useful as the theory for lossless compression. Like if I give you like for lossless compression, for an IID source, you know how to achieve the entropy within 2 bits using arithmetic coding, for example, right? But in lossy compression, there is no such simple algorithms, unfortunately. So that's one thing. And the other thing is like you don't even know the fundamental limit for, if you go beyond the Gaussian distribution, you go to like some other distribution. Oftentimes, you can only estimate the rate distortion function. However, it still gives you a lot of good insights, right? And as we saw, like in the design of JPEG, it was a like very nice mix of theory and human perception, right? So oftentimes, like you start with the theory, then you bring in human perception. Not anymore. Nowadays, you just do machine learning, but like in the olden days, yeah. This is not correct, right? Even in machine learning, you need to understand the theory to like do things, but yeah. So, and then we looked at image compression for a few lectures. So we looked at JPEG, we looked at ML-based image compression. Some of you might have gotten like an intro to transforms, signals and systems, DCT. And we looked at a demo on audio compression. And today's lecture, we looked at video compression, right? And as you might have noticed, like you keep seeing this block diagram many, many times, right? So you start with something, you transform it to decorrelate it. And then in the cases of images or audio, you apply some sort of quantization. In case of video, there is this residual thing happening where you try to subtract, compensate for the motion and so on. And after you do this quantization, which is the only lossy part of the equation, you do some lossless coding. And here you can use any of your lossless coders. And in fact, PNG uses LZ77, JPEG uses Huffman coding, and so on. Like the new ones use arithmetic coding or ANS. And it's a big topic, right? Even the things we covered, we couldn't cover in full detail. Like video compression, this was just a very initial basic flavor, right? Image compression, we just talked mostly about JPEG, but JPEG is now 20 years old. So, and there were the topics that are very exciting that we didn't even get to. So, for example, distributed compression. If you have multiple sensors, multiple nodes, they want to compress their own data, but their data depends on each other. So how can they compress it together? Right? And actually the puzzle in homework 3, the one where you wanted to send X and the other guy had Y, gives you some sense of how to do this. And this actually ties into the other part of information theory, which is error correction coding. And the tools from error correction coding are used for distributed compression very often. Another thing we didn't look at as much is succinct data structures, which is, so the way we thought about compression throughout the class was you start with an uncompressed file, you compress it, you keep it in cold storage, then you bring it out, then you decompress it, right? But oftentimes, I guess the first time you saw something different was today in case of videos, where you saw that you have a large video file on YouTube, and you suddenly want to seek to a particular spot in the video. You don't want to decompress the whole video to do that. You want some level of random access to the video. But this happens a lot, right? Like I have seen it in genomics a lot, where you have like a lot of genomic data and you want to search over the data very quickly. But you also want to store it compressed, right? So you want to get the benefits of compression without losing your ability to randomly access the data or do some operations on the data, right? So this is just like one big field of succinct data structures. And one thing we saw a little, but not as much as, I think Tsachy likes to call it like compression for hardware, in hardware, or like compression for neural networks, of neural networks, by neural networks. So I guess we did see compression using neural networks, right? But there is a corresponding thing where you have a neural network model. Some of you who might have been following like the recent LLM trend might have seen that people are trying to quantize the models, right? They're trying to sparsify the models, do all sorts of things to make the models smaller, right? And oftentimes like various ideas from compression are useful there, also from optimization. So you want to do it in a way that does not lose accuracy. So it's a form of lossy compression where the distortion is not human perception, right? There is no human perception related to like the weights of a neural network, but the distortion is the accuracy of the model, right? You want to lossily compress it in a way that it does not lose its accuracy. Another thing is compression in hardware. So we saw today that the Apple chips, for example, or most of these processors have a dedicated video coding hardware. Similarly, like Z standard, like one of the reasons it's so much faster than gzip is that it can use dedicated instructions. It can use special SIMD instructions. So that's a big field basically. Like, how do you use the existing instructions on your processor to make compression faster? We have some projects which are doing compression on a GPU, for example. And the corresponding thing is, if you have a compression problem, can you then design specialized hardware that can improve that particular algorithm? And then we mostly stuck to like general purpose compression, except for image and video, which is like very big. But there are like a lot of work on special domains, right? So AR, VR is one. I think Pulkit briefly mentioned it, where like if you have this virtual reality headset, right, you are transmitting huge amounts of data to the headset. It's like a 3D model of the thing, and you want to be very intentional about how you compress it, right? If the person is looking at this spot in their VR thing, you use more bits on the part they are looking at and less bits for the part they are not looking at. So like people optimized like very fine-grained way to get the best. Basically, you want like the headset to not heat up and the wires to not be super thick and so on, right? So compression plays a big role, right? I don't know about the Vision Pro. Maybe Kedar can tell us about some secrets, but I'm sure there was some compression somewhere in there. Similarly, genomics, right? It's a very rapidly growing field, and I got my opportunity to work on genomics for most of my PhD. Lots of very interesting applications there, both in terms of compressing things and sometimes losslessly, sometimes lossily compressing things, and also being able to compress while maintaining random access, so sort of like succinct data structures. So, and so on, right? Like people here, I think, are working on a few different domains. We will see on Wednesday with the projects. So, yeah, some part we got to, some part we didn't get to, but hopefully you enjoyed it. So what next? So if you liked the class, even if you didn't like in any case, there are these resources available to you. One is this Stanford compression library. you have used it for your homework. There are parts you might have not seen as part of the homework, so we will try to keep improving it over the years, and hopefully some of your projects we want to include as, basically if you create a merge request, and we do want to include some of that in the library itself. And the whole idea is to make something that's easy for people to use, and easy for people to use, experiment with, and understand. Right. A lot of it started with us wanting to understand how arithmetic coding or ANS or range coding works, and running into like very optimized C code where people don't even want to write they don't even write and like a normal beginner programmer. They just like combine everything into a weird bit mask thing. Very, very hard to interpret a lot of that code. So we made an effort, and it's been useful for us to teach the class, if nothing else, and hopefully it's useful to some of you. The website has some resources. Take a look. We hope to keep updating it over time. And then there are other classes at Stanford which you might find interesting. So EE276, Information Theory, is like the first few lectures of this class will be common, but then there is a lot more theory. You will get much better at the basics. Tsachy, are you teaching it this year? Okay. So Tsachy will be teaching it this year. Right, and especially in lossy compression, I think you will see much more theory. EE376, Topics and Information Theory. I guess that there used to be a series, EE376 ABC. E376C was the first course I took at Stanford when I came to Stanford. It was called Universal Schemes in Information Theory, where we actually proved that like LZ78 achieves the entropy rate for stationary sources and like even more powerful finite results. I don't know if there is a plan to. Is there a plan?
There's a plan, but
okay.
not a good time.
Okay. So yeah. If you're at Stanford when that happens, take a look. For those who are interested in music audio, there is this class called Music 422, which I think is running this year. Please check. Right. We looked at a bit of audio coding in that one notebook that Pulkit showed, but there's much more. There is a lot of psychoacoustics type things. A lot of human perception comes in, and if you look at like the MP3 or AAC or any of these codecs, they're pretty complicated. They do a lot of things to like optimize things. And in fact, like audio coding is also one of those domains where recently machine learning based methods, particularly from Facebook, have been like very, very influential. And finally, this class, which is not strictly on compression, it's on modeling, probabilistic graphical models. And I would say like in today's day and age, even CS236, which is on generative models in AI, those might be useful for you, because we talked about like if you have a good model, then you can build a good compressor. But how do you get the good model? How do you actually find a good model? And that usually comes in terms of either this sort of more probabilistic techniques or more machine learning type techniques, right? So my journey in compression basically started in 2016 when I joined Tsachy's lab. I had no idea I was going to do compression in my PhD. He gave me a problem. I started with it. It's coming to sort of an end now, but hopefully I will come back to it and I will be in touch, definitely. So thank you. Hopefully you enjoyed. Thank you to all the instructors and to the students and the TA.